And in a problem like this, there's a force portion of this problem and there's a torque portion of this problem. We've done this force problem quite a bit before. So if the pulley weren't a massive pulley, you should be looking for something like mg sine theta somewhere in your answer. The fact that there are people out there who don't have the angle worked up in this anywhere suggests you don't remember inclined plane stuff at all from first semester. And there's like 8 of you who are in that boat right now. So that's a concerning number when there's only 32 of you in the room. So let's start the problem by considering that the box on the platform is experiencing 3 forces, but I've done this problem enough times where I feel like I only have to state that there's mg sine theta down the ramp and tension up the ramp. Do I need to actually go the whole route and drawing mg straight down and put a coordinate system on it and break it up into its components? Because if I do, I will, but understand that that's a problem, right? But if you can't do it, you can't do it. So do I need to lay it all out? Okay, so no one's going to come at me later today saying lay it all out. Those are the only 2 forces that matter for that mass. If there were friction, I'd probably have to look at the normal force. But as there is no friction, I don't have to look at that. So I'm going to say net force in the x direction is equal to 2ma. And that'll be 2mg sine theta minus tension equals 2ma. That's for the box on the table. And clearly I've made this way the positive direction. So that also means that this way is the positive direction for that mass. I'll do the net force problem on that mass as well. Here's where I realized the 2 tensions have to be different. So I probably should make one of the tensions, say T1, and one of the tensions T2, because my pulley has mass. That's where this problem changes from first semester to second semester. And I'll have T2 minus mg equals ma. That represents the forces acting on the hanging box. Any question about that or anything that's weird here that we've never done before? Had this been first semester, you'd set those 2 equations together and solve for your acceleration. But the pulley has mass. So now I have to deal with the pulley. The pulley is experiencing 4 forces, but only 2 of them cause torques. It's important that you understand that the pulley is experiencing 4 forces. So don't forget that. The pulley has weight. The pulley is experiencing a force in that direction from the pivot point. They could ask about the force from the mount on the pulley. I don't want you to neglect that. But it also has tension in that direction, tension in that direction, and I've set this direction as the positive direction. So because of that, I'm going to deal with the net torque on the pulley to equal I alpha. There are only 2 torques, and because they're on a pulley, they act at 90 degrees. And their torque arm length is the radius of the pulley. So that'll be RT1, which is in the positive direction. It's causing a rotation that is out of the board, minus RT2, that's from the weight that's hanging, that's causing a rotation that is into the board, and that equals 1/2 3m r squared. That's the moment of inertia of a pulley, putting the 3m in for the mass of the pulley, times alpha, but I'm going to go ahead and substitute A over R because it's a pulley question. It's very likely that it's going to rotate. It's very likely that the motion of the outside of the pulley is directly related to the motion of the 2 boxes. Yep.
How can we say that both tensions are like sine 90 if one of them is at like...
It's about the angle it comes off the pulley. So remember, for all pulleys, the string will wrap until it's coming off at a tangent. So it's always going to be coming off perpendicular to a torque arm. Does that make sense? Okay. I can clean this up a little bit. I can get rid of all the R's. because as you can see, they're all going to cancel out. So getting rid of all the r's, I get, and that's the advantage of putting it in terms of A, is you get rid of all the r's. You won't always get that. And like I said, these are our early problems, but I'm done waiting for us to get to the good stuff. Well, the other stuff where you don't get to cancel all that stuff out. And the problems are maybe more about something a little awkward. These are all pretty straightforward. These are standards. So I cancel out all the r's and I get T1 minus T2 equals 1 half times 3 is just going to be 3 halves MA. I now have three force equations. I don't even have to look at the picture anymore. This is what net force is generated. Any question about these three? This is algebra. The tensions should all cancel if you're adding the equations together, and you should get the net force. There's the pulling of the one box down the ramp, pulling against the other box trying to go down on the side. So you get this little tug of war. And that has to equal the entire inertia of the system. 3 halves M plus 2M plus M all times A. Now, watching your work, some of you start getting sloppy with your mathematics. Just lay it out. Take a little extra time. Look, you're patient with yourselves when you're at practice and rehearsal. Just a little more time here could probably save you a lot of anguish later, or at least save your grade. So let's be a little more patient with our math. I will notice there's an M in every term. And because there's an M in every term, we could get rid of it. But I'm a little nervous that some of you don't see that. So I'm going to factor out the 2mg on this side, which just gives me, actually not 2mg, just mg on this side, which gives me 2 sine theta minus 1. On the other side, I'm going to add all those numbers together. 3 halves plus 2 plus 1. It's going to give me 9 halves MA. Cancel the M's. And I can solve for A. And this is what you're asked to find, the acceleration of the system. It's 2/9 g times whatever this happens to be. What is the condition for the block being pulled? Well, first, is there any question about that? I mean, there should be questions about this because I didn't see this around the room a lot. Have you, in the course of me doing all of this, have you figured out where you screwed up? If so, write something down right now that tells you not what the answer is. Who cares what the answer is? Because tomorrow I'm just going to change this to be something else, and then you're going to be woeful about that. What did you have to do different to get this? Because the next question is the one that you think is inconsequential because it's like the follow-up, but it's not. It's the thing that really decides whether you understand what's happening here. I chose down the ramp to be positive. If this is positive, my acceleration is down the ramp. If that's negative, my acceleration is up the ramp. So not only do I have a condition for theta, but the break point is going to be when it's 0. So when theta is 30 degrees, I'm at a constant velocity. That's where the net force will be 0. If theta is less than 30, it goes up the ramp. If theta is more than 30, it goes down the ramp. Whenever you have an equation where something is being subtracted, you should consider what happens at 0 and when it's negative and when it's positive. Because that's what AP is going to ask about. So you understand that T2 does not equal mg. Okay. Well, no, it just doesn't equal that because it's accelerating. T2 is, if my assumption is right, and that the block is going down the ramp, then this block is being lifted up, right? It's accelerating upwards, which means the tension is greater than the weight of the block. That's the only way it accelerates upwards. Does that make sense?
Also, it's only for statics that it's mg is the force that's hanging.
Yeah. So in this case, it's not static. So this tension that's acting on the pulley has to be the same as the tension that's acting on the block, and it has to be greater than the weight of the block. That good? All right. I have something else I want to do today, but it requires a little bit of knowledge that this is what we are expecting of you. So does anybody have any follow-up that they want me to go over about this? All right. Is it too much of me to ask that you can do a problem like this? I know it wasn't in your homework explicitly, but was there precedent in your homework for this problem? Okay. Oops, let's get all that away. I do want to talk about a ramp problem, and this is kind of leading us to our next topic, but we'll have a test here by the end of the week, I think. And I'm showing you what your test questions are looking like. So this one, though, this is taking us into new territory. I want to talk about the situations for rolling. And help me if I'm wrong here. Did we have a chance to talk a little bit about rolling at the end of last week? Okay, so we explained a little bit of the details about rolling. One of the most important details is at this point right here, it stays at rest relative to the surface. So it's not moving. Everything else is moving around it, but it's not moving. The truth is, when an object rolls, it pivots about this point. That's the true pivot point for an object that's rolling, because it's at rest. The rest of the system is moving. Now, I know that you can think of something rolling and consider what's happening about its center, but it might be better for you to think about an object that's rolling as pivoting about this point. What I want you to begin to understand is an object that's rolling still has all the behaviors of an object that's sliding. For example, this object, if there's no friction, it doesn't roll. Friction is required for rolling. Required. So if they tell you this is a frictionless surface, the only force acting downwards on it will be mg sine theta, if it's frictionless. And this object won't roll, it'll slide down the ramp. There has to be enough friction to hold this point at rest against the surface. That's the only way something rolls, is if there's enough friction for that point to stay at rest. So playing around with this condition, what it would take for that to happen, that's nuance. That's tough. For one important reason, this has got to be the static frictional force, which can be any value under μs times normal force. When dealing with an object that's rolling down a ramp like this, we have to assume before we start the problem that there is a certain amount of static friction, enough to hold that point at rest. How much is necessary? Well, that might surprise you a bit. I'm going to ask you a question that you should already know the answer to. And let's see if I'm correct. If I have two, a disc and a ring, and I put them both on the same ramp, which one gets down to the bottom first? Did we do this in class? Did I hold up the end of the table and roll something? Well, then we should. So whether it's a disc, a block, a ball, mg sine theta minus friction equals ma for this system, even though it's rolling. So even if I have two objects that are identical in the way they interact with the surface, meaning they both experience the same upwards normal force, and we know that friction is based on the normal force, the amount of actual friction is different between these two because friction is on a sliding scale. You only get enough static friction to suit your needs at that moment. So as long as we're not up against a threshold, they get different amount of friction. And it should be something you can predict that the disc is experiencing less friction than the ring because the disc made it down to the bottom first. You need to be able to predict that, like reason it out, because you don't have time to do this on a multiple choice question, but you could be asked about it. Now, starting with just that assumption, I want to see if we can figure out what the size of the frictional force is. We're going to compare it between a ring and a disc. So I started the problem out by giving us a starting point. I've said we're going to start with net force. Let's assume both objects have mass of m, but we're dealing with a ring, so I for a ring is mr squared, and I for a disc is 1/2 mr squared. These objects are experiencing 3 forces. So the other force they're experiencing that I didn't draw in is the weight. Now, we want to evaluate the torque on the system. That's clearly going to be a part of this problem. However, we have to choose a pivot point, and I will let the class choose because you're third period. And whatever one you choose, I'm going to make sixth period do the opposite so that you can see both. Do you want to do this from the center of the object or from the point of contact? Okay, so we're going to do point of contact in this class, and I'll make sixth period do the center. I would encourage you guys who are struggling with this to look at both evaluations, okay? So we'll do point of contact here. If we do the point of contact, that means both the normal force and the frictional force do not apply a torque. Right, you can see it from the picture, but I'll zoom in on the picture. In order for there to be a torque, there has to be a torque arm length. And if I'm using this point of contact, both the friction and the normal force act at this point of contact, so neither of those apply a torque. However, there is a torque from the weight. The radius will be the torque arm length, and the weight is the force causing a torque. It's causing the object to roll down the ramp. This is the actual reason it rolls. The friction doesn't actually cause it to roll. The friction merely holds this point in place so that gravity can pull it down the ramp. And I don't have time to prove this to you, but this angle right here has to be the angle of the ramp. It has to be theta. It should look like it from the picture, but it's theta. It is the angle of the ramp. Which means that our net torque equation, which is net torque equals I alpha, is going to have one torque, which is causing the system to go this direction. I'm going to call that the positive direction. And we can even get that from the old right-hand rule. Torque arm starting at the pivot point this way. The force is that way. That's out of the board. Is causing this kind of rotation. The right-hand rule still has to work. So this gives us the torque arm length, which is R, times the size of the applied force, which is mg sine theta. Well, I guess I could section off the sine theta. So mg is the size of the force, and then the angle at which it occurs is sine theta. The 3 parts of torque arm, force, sine of the angle. This has to equal, which one do you want? We're doing it for the disk. We can plug in the ring later. So disk is 1/2 mr squared. And lastly, it's rolling. This condition has to apply for anything that's rolling. Right, we said that's the definition of rolling. All right. That's not everything, but that gives us the acceleration. And once we have the acceleration, we can get the frictional force. Yeah.
Should we use the parallel axis theorem for doing dividing?
Ah, good point. I was thinking center, and we were going to have to use the parallel axis theorem. We shifted it from the center to the edge. You guys see that? In my head, I was sure you guys were going to ask about doing it from the center, so in my head, I'd already prepared that part, but I better shift it. I guess I can't predict you guys as well as I thought. I really did. I really swore you guys would say center. So I want to clean this up. I can get rid of all the R's. That's still a thing. So let's get rid of all the R's, and we'll get mg sine theta equals 3/2 ma. Cancel out the m's, and I get my a is 2/3 g sine theta. Now, in your head for just a minute, I want you to think about this 2/3. This comes from the moment of inertia. Do you see it right there? If this had been the ring, this would have been mr squared plus mr squared. So in a parallel bit of work, we're thinking about the ring at the same time. The ring would have been mg sine theta equals 2ma. And a would have been 1/2 g sine theta. So the ring clearly accelerates slower than the disk. So I keep that in mind because we're trying to find the frictional force, and that's what we're going to do next. The frictional force is going to be found right here. So mg sine theta minus friction equals ma. This is true for both. It doesn't matter whether this is a block or whether this is a ring or whatever. It's going to experience mg sine theta minus friction. So I'll plug in the a for both. Mg sine theta minus friction equals m 2/3 g sine theta. And mg sine theta minus friction equals m times 1/2 g sine theta. This is ring, this is disk. So if you're trying to give yourself notes, we did the net torque equation first and found the acceleration because it was right there. And then we're using the net force equation to find friction. And what you find out if you do this from the center of the object is that you can get the friction right from the torque equation. It's not less work, it's just different work. I want to solve this for friction, so mg sine theta minus 2/3 mg sine theta equals friction. Or mg sine theta minus 1/2 mg sine theta equals friction. So for the disk, friction is 1/3 mg sine theta. And on this side, friction is 1/2 mg sine theta. Two objects, similar surfaces, different friction. Now, in your head, it should be critical to you to understand that different angles produce or require more friction for something to roll. The steeper I make it, the more it wants to accelerate, the more friction I must have to keep that point at rest. That shouldn't be a surprise. We saw that a block, if you lift the angle up high enough, will eventually slide. So even a ring, which could roll, will eventually slide if the angle gets high enough. Now, you guys are smart people. I want to remind you that the frictional force Has to be less than or equal to mu times the normal force. This is still going to be controlled by mu. There are limits. If you start brushing up against this limit, you'll break friction and your object will not roll, it will slide. Probably sliding with some slipping, because there'll be kinetic friction now. It just won't be rolling. That's it. It's enough for one day.